Today, we are mastering the concept of inverse functions, a vital component of the Cambridge International A-Level Mathematics syllabus. In this lesson, you will learn the necessary conditions for an inverse function to exist, the geometric relationship between a function and its inverse, and the rigorous algebraic steps required to find an inverse expression. This topic is fundamental because it connects algebra with coordinate geometry. In your Paper 1 exam, inverse functions frequently appear in structured questions, often worth 5 to 7 marks, requiring you to handle domain restrictions and algebraic rearrangements. Today, we are mastering the inverse of one-to-one functions, a topic vital for Cambridge 9709 Pure Mathematics 1 examinations. A function f of x has an inverse f inverse of x if and only if it is a one-to-one function. For an inverse to exist, a function must be one-to-one, or injective. This means every unique output value corresponds to exactly one unique input value. Think about a standard quadratic like y equals x squared. If we try to go backwards from an output of 4, we don't know if we started at 2 or negative 2. This ambiguity is why many-to-one functions do not have inverses. To check this visually, we use the horizontal line test. If any horizontal line crosses the graph more than once, the function is not one-to-one and cannot have an inverse. In exams, you will often need to restrict the domain. By taking only a portion of the graph, such as the part where it is strictly increasing, we turn a many-to-one function into a one-to-one function, making an inverse possible. Today we look at the concept of inverse functions. The relationship between a function and its inverse is deeply geometric. An inverse function essentially reverses the operation of the original function. This reversal means that the domain of the original function becomes the range of the inverse, and the range of the original becomes the domain of the inverse. This is a crucial fact for picking up marks in Cambridge exams. If a point a, b lies on the graph of the function, then the point b, a must lie on the graph of its inverse. Consequently, the graph of the inverse is a reflection of the original function in the line y equals x. Now let us look at an example. For example, if a function doubles a number and adds 3, its inverse must subtract 3 and then half the result. This symmetry is the foundation of the algebraic method we use to find inverse expressions. To find the inverse expression algebraically, we follow a rigorous 4-step process. First, we set y equal to the function. This allows us to use standard algebraic manipulation. Second, we rearrange the equation to isolate x. This is the most challenging part of the process, often requiring you to complete the square if dealing with quadratics. Third, we swap the variables x and y to write our final expression for f inverse of x. Finally, and most importantly for Cambridge examiners, you must state the domain of the inverse function. Remember, the domain of the inverse is identical to the range of the original function. Without this step, you will often lose the final accuracy mark in your exam. Let us apply this to a quadratic example. We are asked to find the inverse of h of x equals the square of 2x plus 3 minus 4 for the domain x is less than negative 1.5. We start by setting the expression equal to y and rearranging to make x the subject. We add 4 to both sides, then take the square root. Notice we must include the plus or minus sign here. Subtracting 3 and dividing by 2 gives us 2 possible expressions for x. We must choose the sign that satisfies our original domain restriction. X is less than negative 1.5. If we test a value, say y equals 0, we see that the positive root gives negative 0.5, which is outside our domain. The negative root gives negative 2.5, which is inside. Thus, we must select the negative square root. Finally, we swap x and y. To find the domain of the inverse, we look at the range of the original function. Since the vertex of this parabola is at negative 1.5, negative 4, and it opens upwards, the range is y is greater than negative 4. Therefore, the domain of our inverse is x is greater than negative 4. Let's solve this Cambridge-style question. Part 1 asks for the largest value of k such that an inverse exists. To find where a quadratic is one-to-one, we first find the vertex by completing the square. The vertex is at x equals 3. A quadratic is one-to-one only on one side of its line of symmetry. Since our domain is x is less than or equal to k, we must stay to the left of the vertex. Therefore, the largest possible value for k is 3. Now we rearrange for x. Since our domain is x is less than or equal to 3, we must choose the negative square root to ensure our x values remain below the vertex. The range of the original function starts from the minimum value of -11 and goes up. Therefore, the domain of our inverse is x is greater than or equal to -11. In Cambridge examinations, students frequently lose marks on inverse functions due to a few specific oversights. First, many students calculate the algebraic expression but forget to state the domain of the inverse. Remember, a function is not fully defined without its domain. Examiners specifically look for this to award the final accuracy mark. Second, when solving quadratics, students often leave the plus-minus sign or choose the positive root by default. You must refer back to the original domain. If the domain is to the left of the vertex, you must select the negative root. Finally, students often try to find the domain of the inverse by looking at the inverse expression itself. While this can work, it is safer and more efficient to determine the range of the original function. If you can sketch the original function, its range gives you the inverse's domain immediately. For quadratics, always complete the square. The x-coordinate of the vertex is the boundary for the function being 1-to-1. A quick sketch of f of x helps you visualize the range and ensures you pick the correct reflection across the line y equals x. If you have time, pick a value for x in the original domain, find the output y, and plug that y into your inverse. You should get your original x back. It is time to test your understanding. Pause the video now and attempt these 3 questions before we go through the solutions. Take a moment to work through these carefully, paying close attention to your domain restrictions. Let's look at the solutions. For the easy question, a simple linear rearrangement gives us x plus 2, all divided by 5. For the medium question, we swap the positions of y and the denominator. Since the original function has a vertical asymptote at x equals 3 and is always positive for x greater than 3, its range is y is greater than 0. Therefore, the domain of the inverse is x is greater than 0. For the hard question, we complete the square to get the vertex at 2, 5. Since our domain is x is greater than or equal to 2, we choose the positive square root. The range of the original function starts at the vertex y value of 5. So the domain of the inverse is x is greater than or equal to 5. First, remember that a function must be 1-to-1 to have an inverse. If it is not, you must restrict the domain, typically using the line of symmetry or a vertex as your boundary. Second, the domain of the original function becomes the range of the inverse, and the range of the original becomes the domain of the inverse. Always state the domain of your inverse function to secure full marks. Third, the graph of an inverse function is always a reflection of the original function in the line y equals x. This visual check can help you verify your algebraic results. Finally, when finding the inverse of a quadratic, always complete the square and be prepared to choose the correct sign for the square root, based on the original domain restriction.